Yes, questions? Let's make our U again.
Should we take the Laplacian? How should we take the Laplacian of systems rather than directly integrating?
How can we take the Laplacian?
How can we take the
integral
Laplacian?
Not take the ordinary integral.
Well, I mean, the Laplacian of a function, you are integrating over what?
Not integrating. Find this one.
Finding.
Laplacian of phi is equal to something.
Laplacian of phi is equal to
4 pi rho.
minus 4 pi rho. What is phi?
Not just using direct integration. No, not Laplacian.
What's the question?
Del.
Del. Divergence of E is equal to 4 pi rho. So what is E? Is this the question? This is not enough to determine E. You see, E basically has 3 components. You have one equation. This is not enough. In certain cases, yes, it's enough.
If it has one component.
Plus, with additional information, you can determine it. For example, the infinite planes. Divergence of E is equal to 0 inside. Now, can we determine E in this case? Now, the question is, what else do we know about E? If you tell me that E is only in the x direction, then you're already telling me that it has one component, but this is additional information. This information doesn't come from the divergence of E. Just knowing the divergence of a vector field is not enough to determine it. You need additional information. But for example, this is an additional information. Now, in this case, the divergence of E is nothing but dE by dx, and we are given that this is 0. So this tells me that E should be constant. Again, it's not enough. I don't know what this constant is. I only know that it's a constant. I need additional information. And those are what the boundary conditions are. You see, if you have a differential equation, that differential equation basically tells you how a function changes from point to a point. That's what the differential equation tells you. It tells you about the changes of the function. Derivative is just basically a measure of how the function changes. But if you want to evaluate the value of the function, you have to know the value of the function at some point, at some region. And then starting from that value, adding the changes, you can obtain its value at an arbitrary point. So you have to have some values. And to be able to determine a vector field, you need if you want to determine it uniquely, you need to know the divergence of the vector field. You need to know the curl of the vector field. And you need to know the boundary conditions. If you know all these three, then you can solve uniquely for the vector field. Otherwise, there are not enough information. Which one?
Integral of minus gradient p dot r
P.
p dot p p.
Hmm.
Yeah. Dot r over r to the 3
So
times r to the 2 times dr d omega.
Oh, this one. So we're calculating the gradient of this one, integrating over the whole volume. So how shall we evaluate?
You would use the gas theorem, but
And it says that this is equal to?
minus 4 pi over 3 p.
So how can we prove this? If it were a divergence, it would have been nice, right? The divergence of a vector field evaluated over a volume, we could have converted it into a surface integral.
Mentioned that we should use general form gas theorem.
Which is?
Integral of gradient sum operation
On?
gradient of gradient sum operation. I mean, it can be
Hmm.
cross
Okay.
on A.
Oh.
Capital A
Hmm.
times dV equals integral of surface integral of and that's the same operation on small a, like theory.
So what does this mean? How can we prove this general relation anyway? In our case, it's that operation is the gradient. How can we prove it for our particular case? Now we said that if we have the divergence of some function, some vector field, then it's kind of trivial. So this is the basic relation. From this we can derive all the rest. Now in this expression, We have the volume integral, but not the divergence. We have a gradient over here. So it would have been nice if it was a divergence, but for it to be a divergence, it has to be a vector field, not a scalar function. So we have to convert this. Well, there are basically two things. P is a constant, right? So can we take P out of this derivative? How? If I take it out, what remains? No, I'm doing the vector. I'm not writing it explicitly. I will be writing a vector relation. The left-hand side is a vector. The right-hand side should also be a vector. So if I take P out, what remains? Well, Pi, okay. Then you're talking about components. PR. P times R. Well, how did R get out of the derivative?
We can also take the divergence of separate.
So tell me the expression.
Divergence P times R.
Okay, the divergence of P dot R you cannot evaluate. It's a scalar function, so it is the gradient at most. It cannot be the divergence. You cannot take the divergence of a scalar function. Is it the gradient?
We are taking the out and we want the right values.
Do the component thing. In terms of component, this is a vector, right? So let's look at the I component. The I component is del I of Pj Rj over R cubed. This is equal to Pj of del I Ri over R cubed. This is Pj times the gradient of Ri over R cubed. Right? So if we put it in the integral, dv gradient of P dot R over R cubed, this is equal to Pj times dv. Well, it didn't really work. Because you see Ri over R cubed, we still have a gradient. We couldn't convert it into a divergence. Let's try something else. Phi, this is a scalar function. How can we convert this to a vector without taking derivatives? Yeah, just pick up a vector, an arbitrary one, multiply it with a vector. Now it's a vector field. What is C? I don't know, an arbitrary vector I chose. So let's take its divergence. Now I can talk about the divergence of a vector field. Well, this will be del I of Ci of phi. This will be equal to derivative of Ci times phi plus Ci times derivative of del I of phi. Well, the derivative Ci is a constant vector. So the derivative is just 0. So this gradient of C times phi, divergence of C times phi is nothing but C times the gradient of phi. So this tells me that if I take the divergence of C times phi, let's integrate it over a volume. This should be equal to, on one hand, this is equal to C scalar product with the gradient of phi, del v. But c is a constant vector, so I can take it out of the volume integral. This is equal to c dot gradient of phi, del v. This is what I have on one hand. On the other hand, I know that the divergence of a vector field, I can write it as a surface integral. The surface integral of c phi dot ds. Again, c is a constant vector, I can take it out. And you see c is an arbitrary vector. And this equality should hold for an arbitrary vector. So basically it tells me that if I take the gradient of a function, which is a vector, and take its volume integral, this should be equal to the integral of that function over the surface. Now, what are we trying to evaluate is the gradient of p dot r over r cubed over a volume. But this is equal to the surface integral of p dot r over r cubed over the surface. Now, p is a constant. I can again take it out of this integration. P dot surface integral of r over r cubed. Let's see, this is, let me take the components out, pi. This is ri ds. Now I have to evaluate that integral. Well, to evaluate it, let's make a simplification. Let's assume that I'm integrated over a sphere with center at the origin. If it's a sphere with center at the origin, this is equal to r I over r cubed being the radius of the sphere. ds is something in the r hat direction. That is simplified? Not really. No? Well, you see, ds is, if you want, it is the omega r squared times r squared. This is ds. I cannot replace the omega by the angle because ri depends on the angles. I cannot integrate over the angles. So I cannot write the omega is equal to 4 pi or 2 pi something. I'm not allowed to do that. So what else can we do? What is our I over R cubed? So this is minus the gradient of 1 over R, the I component. Well, it would have been nice if we could take one more derivative of this thing. Basically, in that case, it would be a Dirac delta. Well, let's see. I have a surface integral. Of some scalar function. If it had been a vector function, it would have been great, right? If it was a vector field, A dot ds, this would have been divergence of A integrated over the volume. This would have been nice, but we don't have that vector field taking the scalar product with S. So can we still do this? Let's see, can we use the previous yeah, in fact we can. This was our relation. So phi is a scalar function, integrate over the area. It will be the divergence of gradient of that scalar function. Well, we can do that. If we do that, this will be equal to, remember, but note that we are talking about the ith component of R only. It's like x over R cubed. So this will be equal to the divergence, no, the gradient of Ri over R cubed integrated over the volume. Now this is a vector field. It's not just a Dirac delta in its own. So what is the gradient of Ri over R cubed? Let's look at the J component. The J component will be del J of Ri over R cubed, which is del J times del I times 1 over R, with a minus sign. So now we have this volume integral minus del I del J of 1 over R integrated over my volume. Now I will make the assumption of a sphere. Integrate over a sphere. And the reason why I will make that assumption is that this is equal to 0 if I is different than J. Can you see it? Well, you see, del I, del J, if you take this derivative, what will it look like? I will have some Ri, Rj's. Some term will be proportional to Ri, Rj, multiplied with some coefficient, which will depend on R. Plus, I will have a term which is proportional to Kronecker delta Ij, with some coefficients. Well, if I is different than j, that Kronecker delta is 0 anyway. If I is different than j, let's say I is the x component, and j is the y component, just for a particular example. There I have the product of x times y. Well, the product of x times y is antisymmetric, is an odd function of x. That factor multiplying x times y is a function of r, which is an even function. So if I is different than j, if I is x and j is y, this derivative is an odd function of x. I'm integrating over a sphere, which is an even range of x. If you integrate an odd function in a symmetrical range, you get 0. Like, if you integrate x from -1 to 1, you get 0. If you integrate whatever you multiply x with, x multiplied by a function of x squared, the integral from -1 to 1 will always be 0. Because in your domain, it becomes as much negative as positive. When you sum them up, you get 0. The only possible non-zero contribution is when I and j are equal to each other. In that case, you don't have the products x, y, which is odd in x, but you get x squared, which is even, which you are integrating over an even interval. So basically, that means del I, del j, 1 over r integrated over the volume will be proportional to Kronecker delta ij. I don't know the coefficient yet. Now the trick will be, what is this coefficient? Well, let's multiply both sides by Kronecker delta ij. If I do that multiplication, what becomes the left-hand side? What I mean? Laplacian of 1 over r over the volume. What is the right-hand side? No, I'm multiplying with Kronecker delta ij, both sides. I had one Kronecker delta ij, now I'm multiplying it with another one. What is it? So summing over j, no, not the Wikibeta. I multiply, summing over j, Kronecker delta ij tells me that only the j is equal to I survives, so I have Kronecker delta ii. What is Kronecker delta ii? 1? I'm always using Cartesian. 3. It is 3. We are summing over I. So this is 3. Well, this is minus 4 pi Dirac delta of r. So what we find is 4 pi times 4 pi, that's the result of the left-hand side, is equal to 3a. So minus del I, del j, 1 over r, del v is equal to 4 pi over 3 times Kronecker delta ij. Let's gather our results. Where did we start from? We started from this one. Then we show that that is equal to this expression over here. Then we had that Ri over r cubed integral. Then we said that that is equal to this one. 1 over r is nothing but the one ri over r cubed is nothing but the ri derivative. Of course, this expression is multiplied by pi. So this integral over a sphere. Then we prove that this is pi. This integral with the minus sign is nothing but 4 pi. Now we are, what are we looking at? We were looking at the, now this is, we were, which component are we looking at? Hmm? This is a vector. No, okay, for the time being, it's just a okay, the vector is the ds integral. Now, there's one thing we are missing. So this integral, we show that it was Kronecker delta ij 4 pi over 3. So this is pj times 4 pi over 3. We are almost there, but we are missing one thing. No, not the sign. Where did we lose the vectors? You see, the left-hand side is a vector. So this one is a vector. We are summing over vectors. If you look at the right-hand side, for each I, this is a vector. For each I. So multiplying with pi, again, it's a vector. The right-hand side is a vector. But when we come here, there are no vectors appearing. So this should have been, have some kind of a vector in it. Or we should say that this is the j component of the above vector is equal to this one. That is probably what we are missing. So we had started with the j component of this one. This is equal to the j component of this thing. So even the j component is equal to 4 pi over 3 pj. So that almost completes our proof. So where did we miss that j component? Yeah, here. You see, here we have the Ri over r cubed integrated over ds. We wrote it as a volume integral, where we have this a gradient of Ri over Rj. Now here we started looking at the j component of that expression. The j component is del I del j of 1 over r with a minus sign. So everything fits. Now what we had proven was the j component of this vector over here, the first vector, is equal to the j component of this vector over here. If the components are equal, then we have this equality. So what does this tell me? Remember, PR over R cubed was the potential of a dipole. If you take the gradient, you find the electric field of the dipole. And the electric field of the dipole just turns out to be P dot R hat minus P over R cubed. If you integrate this over a volume, it is 0. If I'm not wrong. But the integral over volume of the left-hand side is non-zero. the integral of the right-hand side is 0, but of the left-hand side is non-zero over a sphere. In fact, not even over a sphere, over any surface. You see, the right-hand side should be the electric field of a system that has, no. The right-hand side is 0 over a sphere. Basically, using the same arguments, just look at the first term. It's r hat, just take the components. R hat, if you just write it as r vector over r, you get the xi, xj over r to the 5 integrated over a sphere, ri, rj over r to the 5. But that is, unless I and j are equal, that is 0. So the only contribution will again be from r, xi is equal to xj. So you would have from the Kronecker delta ii, you will have the 3. So the coefficient will have that 1 over 3 factor, just like over here. We will have the over 3. We have to move it to the other side. We will have the 1 over 3 factor. 1 over 3 will cancel this 3 over here. So the result of the integral of the first term is equal to the integral of the second term. So the integral of the right-hand side will be exactly 0. But we had said that the integral of the left-hand side is non-zero. It is 4 pi over 3 times p. So what does this tell you about how should we correct the right-hand side? We should make a correction to it. Which, by the way, shouldn't appear unless r is exactly equal to 0. Because the right-hand side we just obtained by taking the derivatives of the left-hand side. And we are free to take the derivatives unless r is equal to 0. At r is equal to 0, there are singularities, we cannot really take the derivative. So we should add something which is 0 everywhere except when r is equal to 0. And the integral of which should be 4 pi over 3 times p. Which is, what is the function that is 0 everywhere except on a single point? We have to add a Dirac delta. Now the integral of both the left-hand side and the right-hand side over a sphere are equal. And since we obtain, in fact, this potential for points who are very far away from the dipole, far away compared to the distance between the two charges, this Dirac delta doesn't appear for a realistic dipole. But it should appear for an ideal dipole, for which the size is 0. So any distance is much larger than 0. Including r is equal to 0 is much larger than 0. So that's why we have to add this term for a real dipole, for an ideal dipole. By the way, another way to see that del I del j of, let's say, any function of r integrated over a sphere, spherical volume, around origin should be proportional to a Kronecker delta ij. Well, it's based more or less the same argument, but just using different wording. You see, if you take del I is a vector field, so that the gradient is a vector. It creates vectors from numbers. So it acts, under rotations at least, it acts like vectors. So if you look at the left-hand side, del I is a vector, the component of a vector. Del J is a component of a vector. So the left-hand side, the integrand, just behaves like the product of two vectors, which we call tensors, under rotations. Now, the sphere under rotation does not change. So the integration region kind of behaves like a scalar, a number under rotations. That's why it's important to take a spherical region, spherical volume. If it's not a spherical volume, let's say, for example, if you have an elongated volume, to define that volume, you need to use some vectors. To define the direction in which it elongates, you have to define some vectors. So the result of the integral will also depend on that vector that you use to define your volume. But if there's a sphere, there's no vector there. It is the same everywhere, no matter how you rotate it. So it's just a scale. In that sense, it's a scalar. So the left-hand side, if you integrate it over a spherical volume, it is a vector. It is a tensor of second rank. So the right-hand side should also be a tensor of second rank. Well, there are no vectors appearing in my integration integral, because the r is a vector, but I'm integrating over it, so the result cannot depend on it. My region doesn't depend on any vector. The definition of my region doesn't depend on any vector. So the right-hand side should be a tensor of rank 2, but there are no vectors I can use to construct it. And the only tensor of second rank is that I have that I can use is the Kronecker delta. That's also a tensor of second rank. So the only possibility is the Kronecker delta. So that's why I use the Kronecker delta. Now, if the sphere was not volume around, let's say, R0, not the origin, but R0, some other point, then this integral will be, well, there will be a function of j, but it's also possible to have the I component of R0 multiplied by the j component of R0. So I will need to determine both this b, a and b, to evaluate this integral. But in our problem, we are looking at a sphere around the origin. There's no R0, so we are left with the only possibility, which is the Kronecker delta. For this result of the integral, it can only be proportional to the Kronecker delta. And the rest is kind of the same. Just multiply by Kronecker delta both sides, so you get an equation for A, you solve it. So how can a single point charge have a dipole moment? Hmm? It does. It might. Hmm? No, I just have a single point charge. Just a single point charge, nothing else. Does it have a dipole moment?
Isn't it monopole?
Is it? Let me ask a different question. Do the multiple moments depend on your choice of origin? It does. So does the dipole depend on the choice of the origin? Under which conditions it depends on the choice of the origin? Not always. Sometimes they do, sometimes they don't.
Center of gravity is not the origin.
Yeah, we don't have any gravity here. I mean, why should we talk about center of gravity anyway?
So if there is no gravity, then it doesn't depend on our origin.
It does, sometimes. Let's see. I mean, if you are not sure, just prove whether it depends or not. Let's look at the dipole moment. How do we define the dipole moment? What's the definition of the dipole moment for an arbitrary charge distribution? Hmm?
Time roll.
Now, if I shift my origin, that just corresponds to R goes to R plus R0 everywhere. Right? So this will become dV rho of, let me say, rho prime of R is our new charge distribution. Because since the charge distribution also shifted, it's a different function of position, times R plus R0, which is dV rho prime of R plus R0 dV rho prime of R. Well, this is the dipole moment with respect to the new origin. The other one is R0 times the total charge. So this is how the dipole moment changes if you change your origin. So the dipole moment of a system depends on where you choose the origin if the total charge is non-zero. If the total charge is zero, there is no such ambiguity, such dependence on the choice of the origin. So that is why we usually treat, at least in first year, a plus Q charge and a minus Q charge. Because the total charge is zero, the dipole moment is defined independent of the choice of the origin. But even for a point charge, you can define the dipole moment. If you put the origin at the position of your point charge, this dipole moment is zero. But if you shift the origin, this is how you define the dipole moment. It's just its charge multiplied by its position. Now, in general, if you have the multiple moment, lth moment, let's say, corresponding to YLM, then it depends on the origin if it has the previous moments corresponding to smaller values of L are non-zero. But if all the smaller moments are 0, then that moment is independent of your choice of origin. So a single point charge does have a dipole moment if you don't put it at the origin.
If you have the 2 point charges of the same sign symmetry to the origin, does it also have a moment?
Well, as long as you have separated charges. Now you see, you mean 2 point charges. Let's say one here plus Q, the other one here plus Q. Does it have a dipole moment? Let's calculate. Well, how do you calculate the dipole moment? Let's say this is the n vector. What is the dipole moment of this plus Q charge? The above plus Q charge. Q times n. Of the lower plus Q charge, what's the dipole moment? This is minus n. Q times minus n. So it doesn't have any dipole moment. It has a monopole moment. Monopole moment is just 2Q. If you put the origin at the center, it doesn't have any dipole moment. So if you put the origin somewhere else, it will also have a dipole moment. Because the total charge is non-zero, so the dipole moment depends on the choice of your origin. It will have quadrupole moment. It will probably have all the even moments but not the odd moments if you put the origin at the center. Yes, hello. Are you alive? Some sound. A pure dipole or an ideal dipole is the limit that you take the separation to 0. So for that dipole, you have this Dirac delta. Yes, questions? This one, you have a plus 2q here,
Yes.
and
And mine plus Q in U.
on the other side, plus q.
Then do we have both poles?
Yes, the question is this one. So we have this configuration. Where is the origin, by the way? Because the multiple moments will depend on the choice of your origin. At least the dipole will depend. At the center. You put it at the center. This is the center of the origin. So the multiple moments, they were defined as dv, rho, r, ylm. Right. So my claim before was, and this is the other example, QLM is equal to dv rho of r ylm. Omega, this was equal to 0 if L is odd. This was my claim, and I'm sticking with my claim. And none of you ask why. Now there's the other question. Will it still be true in this case? Of course, first we have to understand why the odd moments were 0 in the previous case.
And understand why the first one is 0.
Why?
Because we have odd power of sine and cosine in the odd moments.
So,
So when we add plus q, when we add here to add plus q, and then add minus q.
no, there are no minus q's over there.
Sorry, plus q was the other charge. But the angle is the opposite. Right? So that's why.
One is at sine 0, the other one is sine pi, both of which are 0.
Yeah. So 0 and 0.
Okay, for even powers?
Even powers we have. Okay.
So if that argument was correct, the even power should also be 0.
But did you mean the summation over n?
No? Each one.
Each one is equal.
If L is odd, then QLM is 0 for all M. Or maybe I am wrong. I don't know.
And simply plug in the expression for y then. Should have it.
Well, how many of them would you like to try? Well, at least for the dipole moment, for L is equal to 1, we said that we had shown that it is 0 for all possible values of M. For L is equal to 1.
For all charge distribution or just for this?
Hmm?
For all charge distribution or just for this?
For the above one, odd moments are 0. And your friend was asking, what about the below one? Would it still be true that for odd L, the multiple moments are 0? My answer would be no. They won't be 0. But then we have to understand why. I mean, do you accept the result just because I'm telling it?
I think
Maybe.
here if we put the origin at the center of charge, it will be zero.
In this one?
Yeah.
No.
What is center of charge?
Well, let's
Same
say the
distance or depends on-
same distance.
Does it depend on
No,
the...
not same distance. So we have plus 2 people.
Well, I mean, if you put it not at the same distance, but let's say in 1:2 ratio, then the dipole moment would be 0, but I don't think the higher moments will be. But for the above case, if I put it at the center, all of them will be 0. Not just L is equal to 1. Let's make a change of variables. Let's take x goes to minus x, or let's just give it a different name, u. Y goes to minus v, z goes to minus t. dx, dy, dz would go to du, dv, dt, without any minus signs. There are no minus signs here. And rho of x, y, and z will go to rho of minus u, minus v, minus z. In the first example, if I change the signs of all the coordinates, the charge density does not change because the charges are positioned symmetrically with respect to the origin. So basically that tells me that this is equal to rho of u, v, and z. T, sorry, not z. This is true in the first example, not in the second one. Do you agree? Now let's see, the problem is, what about theta? Theta, x, y, z. Well, basically what I'm doing is I'm taking this point over here to this point over here in the UVZ plane. Well, that means, let me draw it again. This is the x, y, z plane. I have this point over here in the UV and z t space. This point just becomes this point over here. So this angle was theta. Well, this angle is also theta. So this angle over here is pi minus theta. So this goes to pi minus theta. And phi, well, if you look at the xy plane only, initially I had this point over here. In the UV plane, that point becomes this point. So basically I add a pi. Phi goes to phi plus pi. But under these conditions, YLM, pi minus theta, and phi plus pi, this is equal to minus 1 to the power L, YLM, theta and phi. Of course, this new theta and phi are defined in terms of UV and T. So what we had, we started with QLM. This became du, dv, dt, rho u, v, t. We had the same function rho, by the way. And minus 1 to the L, y, Lm, theta, and phi. Well, I can just rename u, v, and t to x, y, and z. So QLM is equal to minus 1 to the power L times QLM. So this tells me that QLM is equal to 0 if L is odd. Now, the critical thing here, well, this property of YLM is the same independent of the charge distribution. This property of the volume measure is the same independent of the charge distribution. What is the property of the charge distribution? So if under this change, it doesn't change sign, just like in our first example, then all the odd moments vanish. If it changes sign, like if we have a dipole, for a dipole all the even moments would be 0. Because in that case, rho, if we make this change, it will acquire an additional minus sign. So QLM will be minus 1 to the L plus 1 QLM. So QLM will be 0 if L plus 1 is odd, that is if L is even. So if we have plus Q charge, minus Q charge, then all even moments vanish. If we have plus Q, all odd moments vanish. Now in this case over here, where you have the plus Q charge and the plus 2Q charge, well, there's no such symmetry. If you replace x, y, z with minus x, minus y, minus z, then rho neither becomes itself nor becomes minus itself. It's a completely different function now. So both the odd and even moments, in general, they will be non-zero. It might happen that for a particular choice of the origin, some of them might vanish, but not in general. You cannot really come up with a general argument.
Charge distribution under the electric field. What is the energy for this configuration?
Which energy are you talking about? Oh, ask them.
So we would say that the integral of phi rho dv.
Mm-hmm.
Okay, but the problem is that we should have a half. Now, the book is justified that we're considering the energy due to the electric field due to the charges outside our charge configuration, outside our extended charge configuration.
Mm-hmm.
But what about their energy with respect to each other? So we should have some extra term there. For the energy of the charges due to each other, not due to the electric field.
Which can be 0.
Why? Under which conditions we can set it to 0?
Change will be constant.
Not necessarily. I mean, if you say that potential is constant, then you are basically throwing away all the interesting problems. In general, a potential distribution will not have a constant potential. For example, you put an atom in an external field. It doesn't have a constant potential.
And something very similar to rigid body positions, configuration doesn't change.
So what happens if the configuration doesn't change?
Inner potential is constant.
Are you convinced? So that's basically the reason why it ignores it. It assumes that the potential doesn't change. Inner energy doesn't change, so it just behaves like a constant. So in any process, it will be the same. So if you are looking at the changes in the energy, nothing will change. Again, back to the example of the atoms or molecules. Usually, intermolecular or interatomic electric fields are very strong. You cannot really change their relative configuration by applying an external force. You cannot change it much, at least. You can change it maybe a bit, but not much. But you can change the general orientation. That is one thing that you study. Or their vibrations, you can modify it. And by seeing which vibrations you can create, or how you modify it, how it rotates, how fast it rotates, then you can say whether it has a dipole moment, quadrupole moment, etc. And that way you can extract information about the charge distribution. And the same holds for the nuclei.
When you say the total energy of the system is the total self-energies of the particles, additional. For example, if they want us the total energy of the charge configuration, and we say it's the addition of all of the charges and self-energies.
You are asking the question.
You are free to ask the questions in your homework.
What do you mean self-energy? So you are isolating a charge from its surrounding and taking the self-energy and finding all the every charge, every function.
We need to bring that charge from infinity to the configuration. It's self-energy.
Usually, I think we use self-energy for the charge over its distance. So the distance between its position and its own position, so zero. That's how we use self-energy. That's how we term it, right?
I don't know. You talked about the distance from itself, which is a distance which is not energy. So how do you relate the distance to energy?
No, I'm saying, sorry. I meant when we sum over all charges, we said that when sum the energy of all charges, we said that every charge should not count the calculation of its own energy, of its own over the potential rate. So, but then we said, okay, we will relax this condition, and we'll say that since this energy exists always, so if we move it, we want to have, if we move it and we are interested in the difference, then it won't count. That's what we meant by self-energy.
Yeah, that's how we basically define a constant energy, which usually is divergent. Usually, not always.
But that's not what you meant, right?
Can you repeat first definition of self-energy?
We can also say the self-energy of a point charge is the energy it has in isolation. That is the self-energy of a point charge. But that's not what you meant, right? No. I mean, you were talking about the work that needs to be done to bring them to their final configuration. That's not self-energy.
Actually, I read the definition from Wikipedia.
Which says,
That as I remember, energy is bringing from infinity to the configuration.
well, you see, what we did was we were talking about point charges. Okay, we are bringing point charges, and then we talked about the energy of the final configuration of point charges. But we never talked about the energy required to create the point charge itself. That would be the energy of that point charge in isolation. And that energy turns out to be infinite.
Mass times.
I mean, what is mass, we don't really know. I mean, if we stick with the expression for electrostatics, that energy turns to be infinite. If you imagine the point charge to be also made up of different parts, and you imagine bringing all those different parts from infinity to that point, then that energy turns out to be infinite, which is not nice.
It's different than MC2.
Well, I mean, there is no MC to the 2 for the time being. Okay. Then, of course, if infinite energy isn't nice, I mean, we can ignore it because it's always the same infinite. So when we are looking at changes in the energy, they always cancel. So we don't really need to worry about it. But another thing we can do is just try to write down, to give some meaning to it. And one attempt was to say that, okay, they are not actually point charges. They don't exist. And the point charge is, I mean, the electron might be a point charge. The atom is definitely not a point charge. It's very small, but it has a finite size. And the quarks are probably point charges. One attempt was to say, okay, in the special case of the electron, let's say the electron is not a point charge, but a very small sphere with charge distributed either on the surface or uniformly distributed over the volume. It doesn't really make too much of a difference. And then you can say, what is the total energy of this system? Well, of course, the total energy of this system will depend on the size of the sphere. And one interpretation was, okay, let's assume that the total energy of this, total electrostatic self-energy of the electron is equal to mc squared. That was one model. And from this relation, you can say that you can extract the value of the radius of the electron. You can say that the electron should have such and such a radius. But then you are no longer have point charges. But that was some interpretation which, well, it looks nice, but doesn't really work. I mean, with the quantum mechanics, now we know that it doesn't work. This is not the only divergence, by the way, in electrodynamics. We have a couple of other divergences, at least when you look at the quantum version of electrodynamics. But it turns out that those divergences, they just disappear if you are just relating observable things. For example, the energy of a system. If you include the self-energies of the electrons, let's say point particles, it's infinite. But we don't care about the energy. We cannot really measure the energy. We can measure the energy differences, and energy differences are finite. So whenever we calculate physically observable quantities, everything turns out to be finite. Of course, we are not happy with the divergences, but nevertheless they seem to be there, at least for the time being. So are the multiple moments real numbers? So you don't seem to be convinced?
What was the question?
The multiple moments, are they real numbers? How do you prove whether a number is a real number or not?
On the iron form is physical meaning, all form is mathematical expression.
Okay, so for the spherical harmonics, what do you prefer? What's the physical meaning of the multiple moments?
Actually, it's two forms.
Okay, so
We know for the first one, it's just the total charge.
mhm.
For the dipole, it's the dipole. The dipole that we know before. For the quadrupole,
It's a quadrupole.
I
So.
don't understand what does it mean. Physically.
Mhm.
Deformation.
What does it mean, deformation? What kind?
The difference between from a sphere.
What kind of a difference from a sphere? It's a particular kind of a deformation.
Sphere is a monopole. If we deform it, contains dipole.
Sphere is perfect, but nothing is perfect. So
Well,
we have some
mhm.
manipulate this thing to be perfect, and there are some additional terms we neglect.
Well, they basically measure the deformation, as your friends pointed out, but they all have a particular kind of deformation. For example, you have the monopole, it's a sphere. A dipole basically measures, if the monopole moment is non-zero, it can measure how the sphere is shifted from the origin. Or otherwise, if the total charge is zero, that means there are positive and negative charges. It measures how the positive and negative charges are displaced with respect to each other. This is the dipole. Now, the quadrupole is, it might be that these is positive and negative charges. Their center sit at the origin, at the same point, so there is no dipole moment. But it might be that, for example, the positive charges are extended in one direction, whereas the negative charges extend in the other direction. You have this system for it. You have a positive plus Q, a plus Q, a minus Q, a minus Q. So this has, the monopole moment will be 0, the dipole moment will be 0, but it has a non-zero quadrupole moment. So you see, these are the positive charges are deformed in one direction, the negative charges are deformed in the other direction. So this has the quadrupole moment. Or you can go ahead and say, look at this configuration. Plus Q, plus Q, plus Q, plus Q. And let's say I have minus Q's over here. Minus Q, minus Q, minus Q, minus Q. This will have 0 monopole moment, 0 dipole moment, 0 quadrupole moment. It will have an octupole moment. Well, let's say it is kind of the positive charges are deformed along these axes. Negative charges are deformed on some other axis. So they measure how the charge is deformed, the charge distribution deformed from the sphere, deviate from a perfect sphere. Now back to the question, are they real?
When it comes to the different levels of electrons,
Mm-hmm.
maybe
They are real. They are real. No clue.
I think they're complex.
They are complex. Come on, you have a 50% chance of getting the right answer. I don't know. Should they be real?
If they are complex, why we are trying to measure these things? If they are not observable.
Are they not? Complex means, are they non-observable?
Or oscillatory.
Not real. Well, the majority seems to be not real. No. Real, real, not real. I mean, 50, try your 50%. Well, not real seems to be the dominant one. Let's look at the quadrupole moment. Well, the dipole moment is real, right? So how did we define the dipole moment? Pi, oops. Pi is equal to dV rho of R, Ri. Ri is real, rho is real, so Pi is real. But let's say Q1M. How did we define Q1M? dV rho of R. This is the dipole moment also, right? Rho of R Y1M. Now let's start with Y10. What was Y10? Something times cosine theta. Y11.
Something that you
Y1 minus 1. Something times sine theta. e to the power minus I5. Well, why? So Q10 is real. Q11 and Q1 minus 1 are not real. It basically depends on your choice of basis. So which coordinates would you like to represent them in spherical coordinates, in Cartesian coordinates? It depends. They are, of course, related to each other. For example, P3 is proportional to Q10. P1 and 2, they are proportional to Q11 plus or minus Q1 minus 1. It depends on which coordinate system you want to use. They can be real, they can be complex. QLM, in terms of spherical harmonics, in general, they will not be real. Of course, there are the ones that are real, that will be real, like m is equal to 0 will be real, because YL0 is always real, but the other ones will not be real. In Cartesian coordinates, well, everything is real, so the moments are also real. Now, we will also see some other cases where it's easier to work with complex electric field, for example. There we will be working with complex electric fields. For mathematical simplicity, basically. Of course, it might be also that rho is such that the complex ones are 0, like if m is non-zero, it can turn out to be 0, multiple moments. That is the case if the charge density doesn't have any phi dependence. If it doesn't have any phi dependence, then the phi integral will just give us 0, unless m is equal to 0. But for a generic case, the QLMs will be non-zero, will be non-real. And since they are not real numbers, they are not equal to their absolute value, or their real part is not equal to their absolute value.
What if we try to equate the Cartesian form of the animal monopole with the spherical form?
Yes?
What does the imaginary part correspond to? I didn't get any.
Well, you see, Q11 and Q1 minus 1, they are complex numbers. And in fact, QLM is equal to QL minus M complex conjugate, if I'm not wrong. Maybe, no, they should be equal. So you see, Q11 plus Q1 minus 1 is nothing but the real part of Q11. That is Px. The imaginary part of Q11 is Py. The real and complex parts, they correspond to the real and imaginary part, the x and the y components. And in fact, I mean, the z is something different. Here we have the z component. Z component is equal to the m is equal to 0 part, which is real. So in fact, the identification is, you see, the z is equal to r cosine theta. No, r sine theta, r cosine theta. X is r cosine theta, cosine phi, which is, no, x is r sine theta. Cosine phi, which is the real part, of r sine theta e to the power I phi. And y is equal to r sine theta sine phi, which is the real part of r sine theta e to the power, no, imaginary part, e to the power I phi. In fact, you can put the plus or minus signs here also. If there is a minus sign, you put a minus over there. Or in a different way, you can say that e to the power I phi plus or minus, this is actually x plus or minus I y divided by r sine theta. Or sine theta e to the power plus minus I phi is equal to x plus minus I y over r. Well, this is y1 plus minus 1 with some coefficients. Now, when we study polarization and when you study angular momentum in quantum mechanics, you will see that these YLMs, they play an important role. These complex electric fields will be states that have a definite angular momentum. Well, they are complex. We cannot measure the electric field directly, but we can measure the angular momentum. You are taking quantum mechanics this semester, right? Next semester. Yes, other questions?